All right, let's look at this particular problem. An isotope of technetium emits radiation that's detectable by conventional X-rays. So it's useful as a biological tracer. Technetium changes into another isotope of technetium through a first-order reaction. So this is a first-order process. So the first-order kinetic equations are going to apply. So here's the chemical equation for what occurs. Excited state technetium goes to ground state technetium, and it gives off radiation that can be detected. And they give the rate constant K for this process. If 20 grams of excited technetium are injected into a rabbit at a particular time, how much will remain after 2 days? So the equation we want to use for a first order process that discusses the amount of material left at time t is the following. The amount of the material left at time t is going to be the amount present initially times E raised to the power of the product of the rate constant times time. Of course, we're going to take the negative of that. And we have all this information. We have the original amount of technetium, 20 grams. We have the value of E. We know what that is. The rate constant is 0.116 per hour. And we know the time, 2 days. So we have all the information we need to find out how much is going to remain after 2 days. Now the only issue is that our time interval and our rate constant, those units aren't talking to each other. It's pretty easy to convert days into hours, right? 2 days is 48 hours, right? So 2 days, 1 day, 24 hours, that's 48 hours. So this should be fairly straightforward. So the amount we're going to have left after 48 hours is going to be the amount initial, 20 grams, times E to the negative K, 0.116 per hour, times the time, which is 48 hour. Inverse hour cancels hour, which it should be, because anytime you take e to the power of something, it should have no units. And at this point, all we need to do is the mathematics. So I'm going to go ahead and calculate what's in the exponent here. 0.116 times 48. That's 5.568. So the amount present after 48 hours should be 20 grams times E to the negative negative 5.568. We're going to make this negative, and then I'm going to take e to the power of that, which is this button right here. So this is e to the negative 0.5668. That's that value, so that's this. And I'm just going to multiply that by 20. 0.076 grams, or 76 milligrams. Okay, now we're going to answer the second part of this question, which is how long will it take for half of this excited state technetium to decay away? So we'll use our equation, first order decay equation. The amount of time t is going to be the amount initially times e to the minus kt. This is a common question, by the way, with first order kinetics, asking how long it takes for half of the original substance to get converted. This is known as the half-life of a first order process. In our case, it's pretty easy to see that the amount present at time t that we're looking for is going to be 10 grams, right? That should be equal to the original that we started with, 20 grams, times e to the minus kt. So we divide both sides by 20 grams, and we get 1/2 equals e to the minus kt. This equation here will always show up. It'll always be the case for a half-life problem, because you're always going to end with half of the amount you started with. So it doesn't matter if it's like 100 here or 60 here or whatever. After you do this first step, it's always going to look like this. Now, how do we proceed here? I want to get time alone. That's what I'm looking for. I mean, I have the rate constant, so I know K, I know the value of E. I've got half, I got everything but T. How do I get there? What we're going to do is we're going to take the inverse of e to the power of. to get it to cancel out. So there's a law that's known, a mathematical law, that the natural log of e to the x is x. They're inverse functions. And because of this, we can say that natural log cancels the e, and we're just left with the exponent. So that's what I'll do. I'll just take the natural log of both sides of this equation. So the natural log of 1/2 is going to be equal to the natural log of e to the negative kt. These cancel, and I get the natural log of half is minus kt. And then it's easy to solve for the time. We're just going to divide by negative k, and we find a general expression for what's known as the half-life. The natural log of 1/2 over negative k is going to be the half-life, the time it takes for half of the substance to decay away in a first-order process. Well, the natural log of 1/2, that's just a number. Let's find out what that number is. So I put in 0.5, and I take the natural log of it, negative 0.693. So negative 0.693 over, in our case, the rate constant is 0.116 hours, over negative 0.116, I should have said inverse hour. An inverse hour on the denominator is an hour, which is good because I'm looking for a time. So the half-life is going to be 0.693 divided by 0.116. 0.693 divided by 0.116 is about 6 hours. So it takes a little less than 6 hours for half of the original material to decay away.